remember to record this. And so we were talking about filters and resonance on Monday, and so and that was effectively chapter 20. So today we're going to go ahead and get into chapter 21. Okay, and so one of the things they actually start off with in chapter 21 is they start talking about logarithms. And before we really get into that, I wanted to kind of discuss why they get into that. Okay, and so I've got over here a circuit. Let me share this circuit over here. So we've got this circuit with there it is. Okay, so so here's just a simple RC circuit at this point. I don't have an inductor in it, and actually for most of today's discussion we'll probably be just talking about RC circuits. Okay, but so you see here we have Vn, which is our voltage, our source voltage, and just for convenience I made this 1 volt with an angle of 0 degrees. Okay, so it's an AC 1 volt angle 0 degrees, and we're going to feed in you know, so this is going to feed in current now through the capacitor, through you know, and effectively it's a series circuit, so that current is going to flow through the resistor here. But what we're going to do is we're effectively kind of measuring this output, or considering, you know, how much voltage is here at this node V out. Okay, and so if we look at a simple voltage divider, then, you know, we know that the voltage V out is equal to the voltage V in times Z2, where Z2 would be the resistance impedance currently, but I've just left it generic as Z2 and Z1. Okay, so here, let me just label these. So right. So this value here is going to be Z2, because we're going to be interchanging the capacitor a little bit later on. So the capacitor and the resistor and where they're at. So we have this impedance Z1 and this impedance Z2. And so if we then take the voltage N, right, and divide by voltage in on both sides, then we get this ratio of voltage out divided by voltage in. Okay, and so we're comparing what we've got coming in. Okay, this is what we've got coming in, and then we're looking at, okay, well, what are we getting out? And so this ratio then gives us the you know, this ratio V out over V in, you know, kind of gives us what that voltage out is going to be, right? And then if we go a little bit further, if you remember, right, power, and I'm talking real power here, P, okay, so real power P is equal to the voltage times the current. Okay, and so if we kind of look at that, we could say, well, since the current I is V divided by R, then I could say that the power is equal to V squared times R. So then we could say, like, okay, well then if that's the case, then we can say the power, if we assume like a resistance of 1, all right, so let's just say we're gonna let resistance be 1, okay, or the impedance okay, so our resistance of 1, then we're going to get that the power out we'll get power out, right, is going to be V out squared, okay, and power in is going to be V in squared, okay, because the resistance is 1 here, right? And so if we kind of look at this equation over here, okay, we can kind of say, well, the ratio of the power out, so we can take, this ratio of the power out over the power in, okay, it's kind of like saying that's equal to V out over V in. Okay. All right. So again, we're just kind of, assuming the resistance is 1 or something here. This is just giving us kind of a reference point. Okay. So the reason that we can assume, or that we are assuming this, is we're just getting a reference here of how the output compares to the input. Okay. So if R was 1,000, as long as you have the R for the power in equal to this R as the power out, then that ratio is going to be the same. The R piece would cancel out. So that's just kind of, for simplification, I'm just going to say we're going to make that 1, okay, for right now. But so the thing is, though, right, this is really just a simple voltage divider circuit, okay, to get this ratio, right? So we're doing a voltage divider and we're looking at the ratio, because kind of what I talked about on Monday is what we're looking at is, well, here is my antenna or whatever that's receiving these radio waves coming in, and we're feeding it through a filter system, okay? And actually both of these are still the filter system. Z1 and Z2 are the filter system. And then we're generating this output. And then this output, then we would then feed into an amplifier, or most likely we're going to feed that into an amplifier, and then out of the amplifier through our speakers, right? But we want to select a certain amount of frequencies to kind of go through, just like we talked about on Monday. And so what we're looking at is this ratio, how much power are we getting out, divided by power in. And so they basically define a decibel. So if you're looking at, and you see this like all the time with any kind of amplification equipment, or any anything that is doing filters or whatever, they reference this concept of a decibel. All right, so and technically, they actually define something called a bell. All right, and so the bell, just capital B, a bell, is defined, and this is, if you got your books open, this is page 961 in your book. All right, but it's log base 10 of this power over power in. I'm just going to grab it over here. Okay. All right, so this is log base 10 log of power out over power in. All right, so that's the definition of a bell. And so what we're basically doing is looking at this power and seeing this ratio of the power. Okay, so if you assume, again, if you assume like what I gave you up here, that the voltage is 1 volt as the input, as your reference, then, you know, so power in, since power in is Vn squared, but Vn squared is just 1 volt, right? So you're basically just getting, you know, whatever your power out is, okay? But this is the definition of a bell, which is why they kind of go through review of logarithms at the beginning of the class here. But you take this, you know, and this, what this has given us is just kind of it's given us a number, which the unit is called a bell. Okay, that's the unit, and it's a measurement of how much strength we're getting out of this filter. Okay, now the thing is that, you know, this bell is kind of a large number. So what we're going to do, what they do is they create a decibel, right? So deci, remember deci is 10. Okay, so they're going to create a decibel, or normally it's pronounced decibel. Okay, but that then, so 1 bell is equal to 10 of these decibels. And so we abbreviate the decibel with a D, lowercase d, capital B, right? Because that's the capital B of the thing here. So typically what we do is we use the decibel as our measurement. So like I'm a sound guy, I run sound for the church and stuff, and so if you look at a soundboard or any kind of at least commercial sound equipment, they're always talking about the decibel. All right, so they talk about the power in terms of the decibel. And so the equation for the decibel, okay, is, you know, and a lot of times, I mean, officially, okay, so officially the decibel is all about power, right? It's about the power that you're getting out. But remember that power is really just the square of the voltage, okay, assuming that the resistance is constant. It's the square of the voltage out divided by the square of the voltage in. All right, and so if we kind of took, yes, to get higher decibels, that's correct, you have to run through an amplifier. So if we, I don't know, come over here and clear this stuff out of here maybe. Right, so what you would do is you would have a box here which would be an amplifier. Okay, so you'd have to run it through an amplifier. To get above 1. All right, so, you know, really the max that you're going to get out of this circuit, the maximum you're going to get out of this circuit is 1. Okay, because you don't have any amplification. So you're either going to be 1 or you're going to be less than 1. So like if you were to look at a soundboard, let me just grab an image. I don't know if you guys have ever looked at soundboards or anything, but just trying to find a good fader example. This one looks half decent here. All right, so here's just a quick snapshot of the faders soundboard. And okay, just check to make sure you can see that okay. So what you see here when you look at this is this is the 0 mark right here, okay? And so actually, a lot of times they'll actually have a negative sign in here. So anything below this is like decibels. So that 10 is actually like minus 10 dB, okay? So this 10 up here is minus 10 decibels. And so anything above this, okay, everything above this is actually would have to be amplified. Okay, but anything below this is just being, usually you use a term like cut, okay, and so you're just attenuation. Or attenuated. Okay, so everything below this 0 line is being cut or attenuated, and everything above the 0 line must be amplified. Okay, so with just a simple filter circuit here, this is what we call a passive circuit. I think I've used that term before in class where I've talked about passive. Capacitors, resistors, and inductors are all all passive devices. They don't have any way to do any amplification, and so therefore, with just a filter like this, you're only going to be down here in this lower, down below the 0. So 0. Now, wait a minute. Why is that 0? Well, that goes back to this log equation over here. Okay, so if you do a log, okay, so remember that we're doing log base 10. So we're basically looking at, you have your, you know, you have something like 10 to, I don't know, the 5th power. Okay, so let's say something like this. So we have like 10 to the 5th power. Okay, so if I have 10 to the 5th power and I take the log of this, so I'm going to take the log of 10 to the 5th, okay, And so if you remember that, the log, base 10 log, so base 10 log of that gives me 5, okay? And so what we're doing is we're basically, what the log is doing, oh, boy, it's easy to hit the wrong button here, okay? So what the log is doing is grabbing the exponent of this, okay? So when we're doing log base 10, our base is 10, and so when you take log of base 10, and this is our base, then you're left with the 5, okay? So that's kind of this log function is getting us the exponent of a number like this, okay? So what happens, though, is if you take what is the log, or, okay, not the log, but let's say you take 10 to the 0th power, what does that equal to? Exactly, that's equal to 1, Alex. Okay, Andrew. So, 10 to the 0 is equal to 1. All right. So if we take the log, so if we take log base 10 of 1, what we're doing is we're grabbing this exponent, which is giving us 0. And so that's why, like, when you look at this soundboard, 0 means you just have straight feed through. So if I got 1 volt coming in, I got 1 volt coming out. So decibels, and in decibels here, this 0 decibel means that you've got whatever's coming in, you're not doing anything to it. It's just passing right through. Okay. And that's where this comes from this log term down here. Okay. Because 10 to the 0 is 1. Okay. So if you do, log of 10 to the 0, you're pulling out that 0 piece right here. Okay. And so that's kind of where these decibels, so these decibels are really simply showing us how much power we're getting through our filter. Okay, how much power are we actually getting through the filter? So that's the idea of the decibel. It's a measurement of that power. Now, you might be like, well, why don't you just say the power? Well, the problem with looking at power is what happens when you amplify really, really large. So, and we get to this issue also with our frequencies. So let's look at some numbers here. Okay, let's say that I have 10 to the 0 is 1. 10 to the 1st is 10, right? 10 squared is 100, all right? Well, what about if I have 10 to the 5th, which is what we had up there above somewhere? Well, that is all right, a big number, all right. And so what happens is we're going up, you know, 0, 1, 2, going up to 5. And so what's happening is we are going up, the numbers getting really, really big. So if you try to plot this, on a linear graph, these little numbers disappear. They get swallowed up by these bigger values. Okay, and so by using decibels, it gives it kind of lets us see a large range in a better format. Another way of doing that is using what we call log plots. Okay. 10 to the 5, 1, 2, 3, 4. Yes, it was. That's correct, Josh. Thank you. Okay. Like to see that you guys are paying attention here. Okay. So I'm going to have to move my comma. Move my comma over there. All right. So yes. So 10 to the 5 is this huge value, right? And it's just you know, it's just dominating these little numbers, and they basically are like disappearing here. Okay. And so when you're amplifying or whatever, and you're, you know, it's just these little numbers just kind of disappear. They're so small compared to this big number. And so that is why they went to this decibel sort of thing here. And they actually, somewhere in the book there, they talked about the guy who kind of came up with the Bode plots. And I thought that was kind of interesting that he was, if I remember correctly, he was from Ohio State. He went to Ohio State. Okay. So, so I thought that was kind of interesting there. But, you know, so when we look at filters, or we look at amplification, which we really don't discuss too much in this class, because we're just talking about these passive elements, so we're not doing amplification. But when you do that, you need to look at this concept here. And like I say, so the reason that we're doing, just one more time, the reason that we're doing these log stuff is because we're just comparing these numbers, 5 compared to 2 compared to 1, instead of comparing these little numbers to this great big number. All right. And so that's kind of why they started off with all this logarithm stuff right here at the beginning of the book. Okay. All right. So let's come back up here then to our circuit. All right. And so really what we're looking at, right, is we want to look at what, I guess I forgot to just kind of, the official power is power out over power in. Okay. So if we do decibels, okay, so that was bells up here. So if we do decibels, okay, so looking at a decibel, then a dB, okay, a dB is defined then as being 10 times okay, so a dB, a decibel, is defined as being 10 times this, because 1 bell is 10 decibels. So actually, So the decibel is 10 times this value. I think it actually, yeah, I was reading that last night and I thought it looked incorrect. So if you have your book open, he's showing us on 22.9 on page 961. He's showing us this equation, okay? But I think that's actually incorrect. It looks to me like 1 bell, 10 bells should be 1 decibel. Okay, that's what this equation is showing here. All right, so here's the bell. He shows us the bell there in 22.8. Right, so that's the bell. And then he shows us the decibel, which is this value, 10 times log. Okay, and so, oh wait, yeah, so the decibel should be 10 times that. Yeah, so he's got that flipped in equation 229 in there. I should have looked at, I kind of questioned that last night when I was just kind of reviewing this material and stuff. So, but anyhow, so so this is the definition of a decibel. Okay. Now, he also then, if we go to the next page there, 962, then he talks about a millidecibel. All right, and so we kind of take this equation here. Okay, so this is my decibel equation. And he says, well, you know what? If we take this, but when we look at power, okay, so if we come over here then, and if we say, well, let's let power N be 1 milliwatt. Okay, so basically here what we're doing is we're assuming that, you know, if we let the power N be 1 and then whatever that is, which is what we're doing in our circuit there because I only had 1 volt. Okay, but now he's basically saying let the voltage N be 1 millivolt, and then the power would effectively be 1 milliwatt. And then he's, so if that's the case, then okay, then what we would have is this would be millidecibels. So they put a little lower m in there to indicate millidecibels. Okay. All right, and but the other thing is as I talked up above, right, where decibels is really all about the power. However, we can't easily directly measure power as easily as we can measure the voltage, right? So if we come back up here to this equation, right, we get that the power is this voltage squared divided by the resistance, sorry. Okay, that's divided by the resistance. I had it up here, but I had it incorrect there. Okay, so we know that we've got this power. Okay, so power is voltage squared divided by resistance. And so therefore we can talk about dB voltage, okay, And because of this square, and I just did this for you right here, right? So if you take the log, right? If you're taking, when you take the log of this, what you're doing is you're basically getting the exponent. All right. And so, you know, so if you take this equation up here, but then we're going to put in the v squared, so we end up getting this right? So we end up getting that the power, or we got 10 times log base 10 of v squared, v out squared, divided by v in squared. Okay. These are squared values. All right, and so he's kind of like putting parentheses around this. And then we're going to square this whole thing. Well, the thing is, when you do this, this 2 now comes over here, and instead of being 10, makes this 20. Okay, so when you talk about your voltage decibels, you get 20 times log 10. That's log base 10. Let me pull that down. All right, log base 10 of V out over Vn. Okay, and so if we let Vn be our reference of 1 volt, then we're, you know, we basically are taking the log base 10 of the voltage out and multiply that by 20, and that'll give us our number of decibels. Okay, and so that's the equation that he's given us there on page 963 and equation 22.12. All right, but what you know, so the advantage of this is, right, we've used voltmeters. It's really easy to stick in a voltmeter and measure the voltage in and measure the voltage out, and then boom, we've got the decibels in voltage form. Okay, which, because there's a 2 here, we're effectively squaring it, so it's really giving us power. So this really is giving us a measurement of the power, but the units, okay, the units of this is dB or decibels. Okay, but it's a measurement of the actual power being passed from the input to the output of some system. So that could be going through an amplifier or through a filter. It could be either one. Okay. All right, but that's kind of this. You know, like I said on Monday, you know, chapter 20 was really talking about filters. Chapter 21 is talking about terminology that we use for filters. Okay, so not really necessarily a whole lot of circuit kind of stuff going on in here, but he does talk about RC filters a lot. Okay, so all right, so that's any questions on this whole decibel thing at this point? Time for coffee break, so I'm asking for questions. All right, so but that's why he kind of started off the chapter with logs and then talks about all this decibel stuff, because decibels are effectively measuring the amount of power in the that's being passed from coming in. It's coming in and going through our system, whatever that system is, and coming out the outs, the out, and we're looking at what is the power. Did the power go up? Did it go down? Or did it stay the same? If the power stayed the same, right, then you have 0 decibel change. Okay, so 0 decibels means that you're getting, doesn't mean you're not getting anything out. It means you're getting out exactly what you put in. That's what 0 decibels mean, right? Because remember, 10 to the 0 is 1. So you got a perfect pass through. Whatever went in, that's what you're getting out. All right, so if we come back then and look at this original circuit, okay, again, all right, and like I say, it could, I use these generic Z's here because we could have, you know, for Z1 or Z2, we could have a inductor thrown in here somewhere. So, you know, it's possible. Okay. All right. Yeah, Josh, hold on just a second here, and let me, I'll address your question here. So, all right. So we could have, you know, there could be an inductor here. And then Z1, if that was the case, then Z1 would be effectively both of these together, okay? Or the inductor could be over here, right? And this circuit, and then you would have Z2 would be both of those, okay? Or you could have any sort of combinations there. All right, so it, you know, it's just the Z1 and Z2 are these generic terms to kind of indicate the impedances, but what those impedances could be is your choice. All right, so now to Josh's question about distortion. Okay, so if you have a signal, right? So if you have your signal here and you run this through an amplifier, what causes distortion? Well, and my drawing causes distortion. Okay, so if you say this is a sine wave, okay, and you're going to feed this sine wave through this amplifier. Now, how does an amplifier work? Well, an amplifier needs power. Okay, so, you know, a lot of times we draw these like generic boxes here and say, oh, well, that's an amplifier. Well, how does the amplifier work? Well, the amplifier needs power. So you're going to have to put in here some kind of power. And since the sine wave's going negative, usually you also got to have the opposite of that. Okay, and so let's just say that this waveform right here is coming in and it's got 2 volt. It's a 2 volt peak system, and let's say that my amplifier is amplifying at a factor of 2. So I'm amplifying by 2. Well, if that's the case, then my output voltage has got doubled, and so it's going from 4 to -4. No problem. Okay. However, let's say that my amplifier is multiplying times 6. Okay, so whatever's coming in, I'm going to amplify that by 6. Well, then ideally, you know, 6 times 2 that gives me my sine wave here. Wasn't a very good one, right? But it should be going up to 12 volts. And then it should be coming down to minus 12 volts. Okay. But the problem is that my amplifier is only putting in a positive or minus 10 volts. And so what happens, it's getting saturated, okay? And so it's actually, this bit here is getting cut off, and instead of having a nice sine wave, these bits are getting cut off. And I'm getting this out. All right, so I'm losing this whole top piece. Okay. And let me put the lines in here first. Okay. All right, so I'm losing these top pieces. And these things are gone. And so I get this squared off sort of sine wave, and that's what causes distortion. Okay, a lot of times they refer to that as clipping. Okay, so and this output here, this maximum value here, which should be 12, is probably going to be about 9.5 volts. Okay, you might say, well, it's going to be 10 volts, but in reality, the amplifier, even though we're feeding it with 10, it's going to saturate at something below that. It might be 9.8, maybe even 9.9 if it's a really good one, but it's going to be somewhat less than there. And that's where you get the distortion, because if you're putting in a sine wave and you're running it through this amplifier, but it's coming out, it's no longer a sine wave. All right, so hopefully that answers your question about that. So let's pull that bit out of here for now. So, but what we're, yes, you're welcome. So, all right, so, all right, what we're trying to do, right, we're dealing with these decibels here. All right, and the decibel is defined as being 20 times log base 10 V out over Vn. And so we're really looking at this. This is the physics of the circuit, which is defined by your impedance here, and Z1, and your impedance here is Z2. Okay, and so, you know, we can look at that. So if we look in this case, I've just got a capacitor and a resistor here. And so let's give these some values. Okay. And I'm just going to pick, I don't know, I'm going to pick, I guess, Z2. To be, say, 1,000 ohms, right, or 1 kilo ohm. And Z1, okay, well, let's say that my capacitor is going to be 0.1 microfarad. Okay. All right. And so then, if that's the case, then of course Z2 or Z1 is 1 over 2 pi times this 0.1 microfarad times whatever frequency I'm going to feed it. Okay. And so, you know, so then when we build, of course, there's a minus j in there if we're looking at the phase angle, right? So it's a vector. So, you know, you can say, don't forget your phase angle. Okay, so there's definitely a phase angle associated with this. All right, so then we get V out over Vn is, you know, 1k ohm here plus 1k ohm minus j divided by this 2 pi 0.1 micro, okay, times the frequency. And so now we got to kind of look at the frequency. And I guess before I go too far, now this is effectively what we call an RC filter. Okay, so this is an RC filter here because there's no inductor. Okay. So this is RC filter, just a resistance and a capacitor. Why do we like these? Well, RC filters are great for two main reasons, at least. Number one is inductors are expensive. Remember, inductors are made up of coils of copper wire, and copper is expensive, and every day copper is getting more and more expensive. Capacitors and resistors in comparison to inductors are much, much cheaper. Okay, and so inductives are expensive and they weigh more. Okay, because all that copper increases the weight of the filter. So an RC filter can just be, you know, you can build an RC, just a simple RC filter like this one here with just one resistor, one capacitor. You know, you could build this depending on the values of these and how many you're buying at a time for, you know, $1 very easily. But when you throw in an inductor, it could easily make that filter a $10 filter or something like that, which, yeah, well, $10 may not be much, but if you're going to build 1,000 of these, right, that price, you know, instead of $1,000, you're at $10,000 or whatever. So if you can get away with just an RC filter as opposed to an RLC filter, adding an inductor in there, you're going to save a lot of money. All right. And so if you remember, we talked about resonance. Okay, and we had the resonance for an LC. So resonance for an LC circuit with inductor and capacitor, we had that resonant frequency, and the book used S for series or P for parallel, but just using the series version of it here and ignoring the resistance in the inductor, it was this 1 over 2 pi LC. Okay, and that was our resonant frequency. However, again, that's for inductance and capacitance. Okay, but if we do an RC filter here, okay, what is the critical frequency? Well, the critical frequency for this RC, so I kind of consider this a pseudo resonant frequency here. Okay, and another term that they use a lot is the cutoff frequency. Okay, so the cutoff frequency. Okay, so the cutoff frequency for this RC filter turns out to be 1 over 2 pi R times C. There's no square root in there. It's just 1 over 2 pi RC. And this is on page 970 of your book, if you're following along in the book. Okay. And he kind of goes through and derives all this for you. But so the key frequency is this cutoff frequency, which again comes directly from the physics of your elements there. Right? So you get this cutoff frequency, which he just kind of calls FC there in equation 22.16, is your comes from what value of resistance did you choose? What value of capacitor did you choose? Okay, and so by choosing those, we get this cutoff frequency. So you see the similarity here, hopefully, right? Very closely related to the resonant frequency in an RLC circuit. Okay, or basically just the LC piece because in there. So so if we're going to build an RC filter, we get this critical equation here telling us what that frequency is. Okay. And so given the numbers that I gave you, all right, then we're going to get that the cutoff frequency is 1 over 2 times pi times the resistance, which is 1 e to the 3 times 0.1 e to the minus 6, right? That'll give us that cutoff frequency there. And so if I pop over to my octave calculator here, I get that the cutoff frequency is 1591 hertz. All right, so that's 1.59 kilohertz for our 3 significant digits. Okay, and so that is this critical frequency. And in a little bit, I'm going to talk about Bode plots, and it's just amazing how those work there with these Bode plots on there. To know this critical frequency, you can quickly sketch the frequency response of that. Okay, so so that is this critical frequency. So what do I mean by critical frequency? That's your half power frequency. Okay, so remember we talked a lot about the bandwidth and stuff on Monday using an RLC circuit when we talked about the bandwidth, and you had this, you had this here where we had the frequency is going in this direction. And so we were looking at this and it was going up and we had some peak value. Okay, so this was for the RLC. Okay, so you had this peak value, which was occurring at or near the resonant frequency. All right, and then we talked about, so this was our max power. And so we said, well, where's the half power mark? And then with that half power mark there, then we defined these 2 frequencies of F1 and F2, which gave us which gave us the F1 and F2, which gives us the bandwidth. Okay. All right. So Josh, you're asking, that's a 1. This is a 1 here, not an L. Okay. So yeah, the resistor, I gave the resistor up here. No, it's a +3, Josh. 1 kilo ohm. Okay. So 1 kilo ohm in octave, when you can put that in, is 1 e to the +3. Okay. It's e to the +3, which is saying 10 to the 3rd, which is 1,000. Right. You got 3 zeros. All right. So anyhow, looking at, like I say, what we talked about on Monday was this RLC filter, and we talked about, you know, this bandwidth and all that, but all that came from the fact that we were looking at half power. When as your circuit gets more complex, you can apply the Thevenins to it, absolutely, or you can. Well, the problem with Thevenin though is Thevenin doesn't give you the voltage divider. Okay, so right here, what we're doing is we're calculating the voltage out. So we're kind of looking at this box. And then we're looking at what is going into the box and what is going out. And Thevenin, if you remember, just gives you series impedance. So, so the Thevenin doesn't really work in there. You got to calculate this V out piece. So you're looking at a voltage divider. So I guess no, we can't really do Thevenins there. So you would have to, you might be able to, I mean, you would have to do some kind of circuit reduction. You know, it might be better to do like a mesh analysis or something to well, but we really kind of are looking for this. So we would have to, yeah, you could, one thing you could do is break it down into smaller boxes. Okay. So you could kind of say, well, okay, let's have, you know, I've got this great big circuit, and then you could say, well, wait a minute, let's break them down into smaller circuits, which is typically what happens as these, you know, systems get more and more complex. We break them down into these smaller systems and boxes, and then we talk about, you know, what is the power in, power out for this box. And then what is the power in, power out for this box? And what is the power in, power out for that box? And then we can multiply those powers together. Okay. So if this was like, if this amplified, let's say they were amplifiers. So this was a ×2 amplifier. And this was a ×3 amplifier. And this was a ×5 amplifier. Then our output would be 2 times 3 times 5, right? Which would be 2 times 3 is 6, 5 would be what, 30. So we'd have a gain of 30 coming out. Okay. So yeah, so a lot of, you know, as your circuits get more complex, if you know, we try to break them down into these boxes, and since we're looking at power and we're looking at the ratio between power out divided by power in, you can look at that and see these amplifications. So these are basically like would be amplification stages or something, or they could be filter stations, which would just be attenuations. But all right, so let's see. So yeah, so we looked at the critical frequency here. All right, and so again, what we are we want to look at this equation here. V out over Vn is Z2 times Z1 plus Z2. Okay, so let me show you a couple of things in octave here. And unfortunately, I'm going to have to kind of switch back and forth on screens to do this. Okay, but if we okay. All right, so in octave, here's my calculation that I just made, right? This was that critical frequency or cutoff frequency equation that I did here. But I'm just going to go ahead and define R is equal to 1 e to the 3, right? So we can see that that's 1,000. And then our capacitance is 0.1 e to the minus 6, okay, which of course is a bunch of zeros there, okay? And so, oops, 1, 2, 3. All right, so it's 0.1 microfarad, okay? And now, the thing is, though, that when we look at this, okay, our V out, now remember, Vn is simply 1, okay? Because that was my original definition. Vn was simply 1. But now I need a frequency. Okay, so I'm going to do a frequency here. And I can actually do a range of frequencies. Okay, so I can build up a range of frequencies. And my cutoff frequency is up here is 1,591 is that critical frequency. So what I want to do is I'm going to go 2 decades below that and 2 decades above it. So what that means is I'm just going to start off at 10. And I want to go from 10, and then I'm going to do 100. And then I'm going to do 1,000. Okay. And then I want to do 10,000. And then I want to do 100,000. Okay. And so I have this whole range. And now if I do this, this only gives me 5 points, which doesn't work too well. So what I'm going to do, there's actually a couple of different programs that I could use. One of them, or functions, not programs, but functions. One of them is called log space. And what I can do is I can tell it to go I can tell this log space to go from 10. Well, let me put this back in like I had it for a minute so we can see these numbers. Okay, 10, 100, 1,000, 10,000, 100,000. Okay, so as you can see here, so this gives me this vector here, and it has 5 values. The first value is 10, 100, 1,000, 10,000, and 100,000. So if we look at these, right, 10 to the first is 10, right? And 10 to the fifth, okay, so this caret means to the power. So 10 to the fifth power is 100,000. So when you do this log space, if I do this log space now, if I do F log space 1, 5, it's actually looking at these powers. Okay, and so if I say just give me 5 of these, it gives me back exactly what I had, which is just these 5 points. Okay, but what I want to do is I want to do 200 of these. Okay, so what this is going to do is it's going to run through and it's going to pull out 200 values between 10 and 100,000. All right, and so here are the values. You can see the last value is 100,000, but I've got 200 of these, and so as you scroll through, all right, we can scroll all the way back up here, and I can see the first value was 10, and then the next value was a little bit more than that, and we scroll down here a little bit. Remember that my optimal value was 1,590. So you see here I got a value of 1,550, which is close to that cutoff. Can you do this in a graphing calculator? Yes. Okay. The question is how? Don't ask me. I don't play with those graphing calculators. Okay, but you can do this on a graphing calculator. All right, but you can graph right here in Octave, which is what I was going to show you. Okay, so here is this. I've got 200 points. Okay, and so I've got 200 points ranging from 10 all the way up to 100,000. And I'll go back and do it like with 1 or 2 points also. All right, but then I want to now calculate my total impedance, which is effectively V out. So remember, V out is or V out under Vn, and Vn is only 1 volt. Okay, but that is equal to Z2 divided by Z1 plus Z2. Now I haven't defined these yet, so these are undefined. Okay, but I know that my V out, the Z2 is simply R, right? And then Z1 plus Z2 is R minus J times this 1 divided by 2 times pi times the capacitance C, okay, times my frequency. Okay, and this will give me these values. Now actually when I do this, it's going to give me an error message. Okay, and this error message is talking about non-conformance, because the problem is that C is just a scalar and R is just a scalar, but F has 200 possibilities. Okay, and so that's what this is complaining about. It's saying operation 1, these are all scalars. Everything here is all scalars, but F is not a scalar. It's a vector with 200 possibility or 200 values in it. And so what we have to do is we have to use this special calculation by putting a dot in front of this. Okay, and I didn't think that would work, so I pretty much just got to come through and do a dot. Anytime I do a multiply or divide, I just need to put this dot piece in here. Okay, and so now you see that I've got 200 values. Okay, so I've got 200 values here, that these are all basically voltages out. Okay, because remember, voltage in was 1. And so I've got 200 possibilities. Now, when I do this, it dumps these 200 possibilities out, and it just goes and goes and goes. All right. So what you can do is one of the things, remember in this Octave software, you can use your up arrow keys to recall stuff. All right. And the other thing is when you're doing a lot like this, you put a semicolon there. It generates that output, but it doesn't display it. Okay. Now what we can do is we can plot this. Okay, so I can come in here and I can actually plot this. So I can create a figure. And if I just type plot, it'll create a figure. So I'm going to plot frequency versus voltage out. Okay. So when I plot this, and this is where we kind of get into here, I'm going to have to switch back and forth between screens. Because when I plot this, it generates a plot. Okay, and the plot looks like this, and it doesn't look very nice. Okay. Because it's not in a log format. But I'm going to show it to you here once I find that screen. Got too many windows open's my problem here. Figure 1, there it is. Okay. All right, so this is what the plot looks like. Okay. And the issue with this plot here part of the issue with this plot is it doesn't, so if you look at the plot, down here at the bottom is my frequency. Okay, and I can actually label these frequencies. I'll show you the code for this in a little bit. But I can label this with something called the X label. Okay, and then I can do something called a Y label. To label the Y-axis, which is voltage out, which of course is in volts. Okay, and so I can label these in there, and we can see that. But what you notice here is that the frequency, it starts at like 20,000. Well, it starts at 0, but then the next value is 20,000. All right, and so this is not a very nice plot. So what I'm going to actually do here is I'm going to create a subplot on here, and then I'm going to plot what we're looking at. And then I'm going to create a second subplot, and I'm going to use something called the semilog on that plot. Okay. Okay, and so when you look at these plots, you see that they're both plotting the exact same thing. Okay, but in the bottom one, we're plotting, you see we have 10 to the first, and then 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth. Okay. And so let me switch back to my paint program, and I can just paste this plot in there, and we can kind of look at it that way. But wrong one. Okay. Did I close my window or what? Here, I don't see it. There it is. Okay. All right, so let me get this pasted in here and then I'll answer your question there. Okay. But let's see, I'm going to post the code so you can see that also. Okay, so here were the commands that did this one. And here were the commands that did this one. All right, and so, all right, so let me look at your question here. Does this graph help show us what frequency we reach maximum voltage? Absolutely. Okay, so remember that our maximum voltage is 1. Okay, so for this, our maximum voltage, okay, so our input Vn was 1 volt. Okay, we have no amplification. And so therefore our maximum voltage out can only be what we put in, which is 1 volt. Okay, and so we can see that there here on this plot here, so we can see that. So the difference here of these two graphs is this one over here. This plot over here, all the low frequencies, remember our critical frequency? Okay. Our critical frequency we calculated, or our cutoff frequency, was calculated to be 1.59 kilohertz, right? So this 1.59, where is that? Well, if we look over here, that's right here somewhere, okay? So yeah, so the question to me is like, well, where is that frequency? Okay, that frequency is lost. It's squished down here in this bottom of the plot. Okay, but if we do this semi-log piece over here, right? So if we run this semi-log, and it's called semi-log X because it's logging in the X direction, right? So down here we're getting this, 10 to the power 1, 10 to the power 2, 10 to the power 3, right? So now, though, what we're getting here is right here at 1.5. Our 1.5 here, here's half power. Okay. So this right here is this cutoff frequency. Okay. And so by doing a semi-log plot, I can get this out here and we can see that ratio and we can see how that plots there. Okay. So this, by plotting this semi-log, we can kind of break these frequencies out and see a better shape. So like if anytime you go out and you buy some sort of device that has a frequency response, they always give you the frequencies plotted in this semilog format. Okay. And so that you can see these values in this sort of format. Okay. And so again, this part right here, this is our half power. All right, so this is the half power line, because remember we're getting right, this is 1, so this is my direct feed through up here. All right, and so this is 0.5 here, this is half of that. All right, and that is where that cutoff frequency is at. Okay, so let's take a minute to try to read this log scale here. I'm going to try to zoom in on this. And so we can kind of read these numbers a little bit better. So let me come over here. The computer's kind of slow responding. I should have shut some of these windows up before I started the thing here. Okay, so there's my figure. Okay, so here's my figure. I know you guys can't see what I'm doing right now. I'm just going to kind of try to zoom in on this a little bit. Let's see if I can blow this up enough that we can read it, hopefully. All right. So this is just kind of a zoom up of the axes here. Okay. And so, all right, remember this is 10 squared, so that's 100. And this is 1,000. And so this value over here is 10,000. Okay. So then when we look at these little tick marks, this first tick mark here is 200. And the next one would be 300. And the next one would be 400. The next one would be 500. Okay. So when we look at these, that's 300, 400, and this one here is 500. So let me kind of shift these a little bit. So that's 400, and this one is 500. This one over here is 300. Okay. And so if I take these and I shift them over here, notice that the spacing is exactly the same, but now these values over here are 2,000, 3,000, 4,000, and 5,000. Okay, so as we go through, right, this is 100, and then the next tick would be 200, 300, 400, 500, 600, 700, 800. This tick right over here, would be 900, and then this is our 1,000. And then we have 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000. And this value here would be 9,000. And then this is 10,000. Okay, so that's what these tick marks mean in here. And so when we space it out in log format, this is what it looks like. But this allows us, therefore, to kind of focus on plots when we have such a large range, right? Because if we don't do that, we end up having, you know, here's all these big high frequencies, all this big range of frequencies from 20,000 to 80,000, where basically nothing is happening. Okay, and so it's all happening right over here in this very small section of the graph. And so the rest of this seems almost pointless. But when you use a log format, it kind of smooths it out there. All right, so that's kind of the idea of these plots. Now, the other thing here is, though, is that I just plotted the voltage in volts. Right, so this voltage here was in volts. The units of this was volts, not decibels. So if we kind of go back through then, and I'm going to do the same plot. Okay, so if I try to like do this exact same plot, but I'm going to change it to decibels. All right, so remember, decibels for voltage is 20 times log of our voltage. Okay, and so then what I'm going to do is I'm going to do my subplot here. I know you guys can't see what I'm doing. I'll show you the commands here for a minute. Let's see if this, hopefully this is looking good. Yes, this is looking good. Okay. And then okay, so I got to try to get a decent screenshot of this now. Not showing up real well, but all right, so now what I've done is I've replotted this using decibels. Okay, so this is what it looks like using decibels. So actually, let me retry that one more time. I want to get both of them together. So okay, so I'm just, let's see, I want to label this. And I'll show you the code that I'm doing here too, so if you want to try to do this, but there it is. Okay. All right, so here is both of them together. All right, so to get the decibels, then here's the code that I used to get this. Okay, and so what I did was I used that equation we had before to calculate the decibels. All right, so this is the equation to calculate your decibels. Okay, so this was scaling of this as dBs. And then, you know, this was my subplot. Now I've on the top subplot here, I put just straight voltage. And then on this subplot, I put the decibels. Okay, so these are the exact same except for the bottom one is calculating decibels. All right, so the bottom one is in dBs and the top one is in volts. Okay, so you can see the difference here. Now it's very interesting because the frequency, again, if I can try to draw this frequency here, as right here is the half power mark, right about here. So my frequency is right along here, if I can get that straight. Okay, so this is that cutoff frequency. Okay. Oh, that's a lovely color. Huh? Okay, so all right, so this is my cutoff frequency here, which is 1.59K. All right, and so what you see right up here, was half power, and here, where is half power here? Now this is kind of interesting. Okay, so this is my half power mark, which is -3 decibels. Okay, so you see, okay, So this is 0 dBs here. The blue line is 0 dBs. And this line here is the minus 3 dB line. Okay. So right here at this point, where it is at 1.59 kilohertz, which is our cutoff frequency, is when you plot it in decibels, it's actually minus 3 dB. Okay, so that minus 3 dB means that you have half the power you had before. All right, so this right here is the feed through 0 dBs. Zero dB means that power in is equal to power out. Okay. And minus 3 dB means that power out, I should have probably wrote the other one the other way. Power out is equal to 1/2 of power in. Okay. So let me flip these two. So, you know, normally we're you know, the question is, how much are we getting out? Okay. And so power out is equal to power in at 0 dBs. At minus 3 dBs, we've lost 50% of our power. Okay. And that just comes directly from the log equation. Okay, so if you look at, remember the equation for decibels is 20 times log times the V out. So V out is half. So let me show you this equation. Here's the octave code for that. Okay. All right, so when you calculate your dB equation, if your power out is 1/2 of your power in, right? So if power out is 1/2, this is power out, okay? And so if power out is half of power in, then you get minus 3 decibels, okay? So that just comes from evaluating this power equation that I gave you earlier. So half power means minus 3 dB when you're plotting in decibels. So, and your book actually talks about that. They talk about sound pressure. Somewhere in there, he gets into the discussion about sound pressure and stuff like that. But he talks about how 3 decibels is doubling positive 3, right? Positive 3 decibels is doubling the power, okay? Or minus 3 dBs is having the power, okay? So if we go the other way, if our power in is twice power out, all right, you can go the, you know, we can go the opposite way. All right, and so here I've got twice the power. Double the power is plus 3 dB. Okay. Half power is minus 3 decibels. Okay, so when you're using the dB values, the decibel values, 3 dB in either direction is either, you know, doubling or halving your power. So that's kind of that critical thing, because if you remember what we talked about on Monday, right, the bandwidth of our filter was defined as being the half power mark. Okay, and so 3 dBs is the half power mark. Okay. All right, so then when we look at this, though, you note how straight this looks. Look at this. This looks really, really straight here. All right, and this looks very straight over here. Okay, and so the only place we have any curve is just right along here. There's a bit of a curve, but the rest of this is really straight. And the other thing I want to kind of mark out about this graph here is if we go from here to here, so we're going down from minus 20 to minus 40, okay? And if we mark that point, and we mark this point, I didn't draw the lines very straight, but notice these little tick marks as your reference point, right? Boy, it's really thick there, but right. So here's a tick mark, and here's a tick mark, and so if I drop these, and again, my lines aren't very straight here, but basically this line dropping down here, okay, is dropping 20 decibels per decade. Okay, so this is dropping 20 decibels per decade, right? It's going from minus 20 to minus 40 in a factor. A decade is talking about going down from, you know, 100 down to 10, or, you know, from, you know, 1,000 down to 100, okay? And so it's dropping 20 dB per decade. All right, and so this is actually, if you look, this is on page, starting on page 987, this is the magnitude of a Bode plot. Okay, so this is the magnitude of a Bode plot. And so he talks, he's got a little biography of Hendrik Wade Bode here, and he went to the Ohio State University, okay, and talks a little bit about him, but he's the one that kind of realized this. And this is just, these Bode plots are really, really cool, because when you look at this plot, and I'm going to paste a new copy of it in here because I've already drawn on it so much. Okay, but you can sketch out a Bode plot in about 3 seconds flat for an RC circuit, because all you got to do is you got to calculate this that cutoff frequency, right? So we take our cutoff frequency here, we find that cutoff frequency 1.59, which is about right here, right? Which is at our -3 dB line, right? And so what you do is you can, you find this cutoff frequency, you mark that point right there, and then you draw a straight line here. And then you draw this other line, which is dropping off at -40 dB per decade, or -20 dB per decade. And this is your Bode plot. So this is the magnitude anyhow. So all you do is draw this straight line to the cutoff frequency. And then you draw another straight line that's dropping at 20 dB per decade. All right. And this difference here, the maximum difference, okay, is -3 dB at the cutoff. Okay. So right here at this cutoff, you're going to have your biggest error of 3 decibels. When you draw, if you just draw that straight line like I did, okay, your maximum error is 3 dB, and it occurs at that cutoff frequency. Okay. And so these Bode plots are just kind of really slick because you can just draw them very quickly. All right, now this happens to be what we call a high-pass filter. Because remember, we stated on Monday that we're effectively passing all filters that are more than half power. Okay, so we're passing all frequencies greater than half power. Okay, and so this is a high pass filter, and so we are cutting frequencies that are losing more than half of the max power. Okay. So this is a high pass filter. So let me see if I can sketch this filter again so you guys remember what it looked like. Okay. So this was, here's the circuit, right? We had our little sine wave going on here. And we had the capacitor up here. This was our V out. And then we had this resistor here, right? So that was the circuit that we had. Okay. And so it's a high pass filter. Okay. All right, so what I'm going to do is if we flip the circuit, so if we were to go over and flip the circuit around so that we had the capacitor and resistance changed, I'm just trying to get this. Okay, so come on, updating. So, all right, hopefully that'll do it. All right, so if we flip it around, there we go. I get the exact same plot, only it's flipped around. Okay, so let me clear some of this out of here. And so right here, I get the exact same plot. And so my cutoff frequency, right, is at 159. So that was like here. Somewhere right around here was that cutoff frequency. And so if I draw this line here up to the cutoff frequency, and then I draw this line here, okay, then this is the magnitude of my Bode plot, a straight line, what we call a straight line Bode plot. Okay, and so with this straight line Bode plot magnitude, okay, again, we're only 3 decibels off, okay, but this here is a low pass filter. So we're passing low frequencies. Okay, and so this is a low pass filter. Oh. And so the circuit, again, the circuit looks just the flip of the other circuit. So we have our input voltage, and now we have the resistor is here. Okay. And that is a low pass filter. Low pass RC filter, of course. Okay. So we have a low pass filter, and the first one that we were doing is here is the high pass filter. Okay. Now, if we then go along and we choose, as I kind of said before to your, forget who asked that question, but we can kind of daisy chain these things together. And so if we were to kind of come along there and build a circuit like this, where we had, you know, here's my input, and then I had my capacitor here, which was a 0.1 microfarad, and then a resistor here, which was 1K. Okay. So if the cap comes before the resistor, it's high pass, and if the cap comes after the resistor, it's low pass. That is true. And the reason for that is, remember that the impedance of a capacitor is, you know, got your minus J there, but it's 1 over 2 pi times C times the frequency. So as the frequency goes up, X goes smaller. Okay, so if F is small, then X is big. But if F is big, then X is small. Okay, all right, and so when we what happens is, for this right here, at low frequencies, this doesn't drop much voltage. Right? At low frequencies, this doesn't drop much voltage, so therefore the voltage is just passed, and this is dropping all the voltage. But at high frequencies, what's happening, if I scroll down here and look at that circuit I just put in, right? At high frequencies, this acts like a short, and so it's basically shorted to ground at high frequencies. Okay, and that's why when we see these, the voltage is just dropping. The power is, we're just losing power. As the voltage gets higher and higher and higher, we're losing voltage because it's shorting out to ground. It's effectively a short. Okay. So if we take this is a high pass filter up here, but now I'm going to connect to it I'm going to take this high pass filter and then I'm going to take and put a resistor here. And I'm going to put a capacitor here. And this is going to be my output voltage here. Okay. And so now I've got a high pass filter okay, which is passing everything 1.59 kHz and above. And then we've got this one here, which is a low pass, which is passing everything below, and I got to calculate that. If I did it right, I expect it to be like 150,000. Maybe that was probably too big of a value. 10. Oh, I went the wrong way. I'm sorry. Yep, I went the wrong way with my capacitor. This is called the capacitor 1. Let's call the capacitor 1 farad. Okay, and so that's going to pass everything below 15.9. Okay. And so what happens then is I'm going to end up with a Bode plot. That's going to look something like this. So I'm going to have it's going to be going up like this, and this is going to be 1.59K. And then it's going to go straight across here. And this is 15.9. And then it's going to come straight down like this. And now I built a bandpass filter, where I'm only effectively allowing these frequencies through. Okay. And I didn't have to use an inductor. Okay, so we did bandpass filters on Monday using an inductor. But again, the problem with inductors is they're kind of expensive and they're kind of heavy. And so they raise the cost. So by taking two RCs, picking my values here, and chaining them together, I can build a bandpass filter and pass a certain band. So like if I wanted to do a radio or something like that, I can still do a bandpass filter even though I don't want to go buy an expensive inductor. Okay, so yes, Josh, the resistor, I made the resistor 1K. Or 10K, I mean. So, you know, over here the resistor was 1K. And here I've increased the resistor, and I also increased my capacitor. And I don't know if I punched that number in correctly. 1e to the 4, 1e to the minus 6. Yeah. Looks okay. Anybody verify that number there, 15K? This should be 15 kilohertz. I didn't put the hertz down either. All right, so this was 15 hertz. Okay, and 15,000 hertz. Okay, so I'm effectively passing. This bandpass filter is leaving about 10,000 hertz pass. Okay, so this band pass is letting like 10,000 hertz pass. Okay, so if you remember, I was actually talking about audio, I think on Monday, and I talked about the range of audio was from 2 hertz, or excuse me, 20 hertz to 20,000 hertz. Okay, so this filter here is not quite wide enough to let 20,000 hertz go through. Okay, and of course the frequencies aren't quite correct either there, but so, but hopefully you get the idea. We get to pick what the R's and C's are, right? We can pick those. And so therefore we can build a filter with any values that we need. Okay. All right, so the one other thing I didn't really talk about here was the phase angles. All right, and so where's my... So if you look on page 991, he kind of talks about the phase angles. So let me just kind of throw a graph on that here real quick to try to grab it out of the book here real quick. All right, so if we look at the phase angle, the phase angle, this one here is the one. Whatever page I'm on here, 991. Okay, so yeah, so this is the plot from the book. Page 991, which is showing the phase angle. All right, so notice here that this is for the high pass filter case, and so the phase angle is going from positive 90 degrees, and then at that cutoff frequency it's at 45 degrees, and then as it goes on down it gets there, and so your largest error occurs at the cutoff frequency divided by 10. Okay, and your error is going to be 5.7 degrees off if you do straight lines, and at 10 times that, so that decade frequency. Okay, so what you do is you to draw the phase angles. All right, to draw the phase angles, I would just come along here and draw a straight line to a decade below the cutoff frequency, and a straight line to the 10 times that frequency, and then a straight line connecting those two. And that gives me a real quick idea of what the phase looks like. And the max error that I'm going to have when I do that is 5.7 degrees, which is occurring at these two frequencies. Okay. And so, because remember, there's always a phase shift too. So what this means is that as these frequencies are coming through, you've got more than one frequency all coming through the filter at the same time. And so the what's happening is that the amplitude of some of those frequencies, right, the amplitude of these frequencies right here are getting cut off. So they're not, even though we say they're being passed, but these frequencies right in here, we're chopping those off. Okay, this was the low pass we're looking at here, but it's just in the screen right there. And so the amplitude of those is dropping some, but they're also, the phase shift, they're getting shifted a little bit. So what does a phase shift mean? Well, if you think about sound, if you think about music, the phase shift means like a delay in the music. All right, because remember that we've got a sine wave. Okay, so we're talking about sine waves here. Okay, we're talking about fast and slow sine waves, but what we're doing is we're shifting them. Okay, so they're getting shifted. That's what the phase shift means, is the sine waves kind of getting shifted back and forth. So if you think about like an entire orchestra or band where you got high frequencies and low frequencies, all the frequencies that you're passing, okay, you're saying, okay, they're all going through, but we are losing energy out of some of those frequencies. And they're also getting shifted a little bit as they go through these filters. So that means they may be a little bit behind the other frequencies. Okay, usually it's not noticeable, but there is a delay. All right, but that covers the chapter 21 for the most part. He gets into some other things. He talks about notch filters, and which is just using narrower filters, and he talks about ladder circuits, which I kind of just showed you. If I can erase everything I just did here. Right, this is kind of a ladder circuit right here. Or where you combine them. Actually, if you combine one high pass with another high pass, then you make it steeper and you make it filter it in even tighter. Okay, so he talks about the ladder circuits in there also. All right, so we got it. Actually, we're about out of time here. So any last questions? Okay. I believe I did hit record, so I could post this so you guys can watch it again if you can't sleep tonight or something. All right, so if not, that's it. So their homework is probably not going to be up today. I will work on it. It just trying to do all my classes online is just taking a lot of time. I'm trying to figure out how to do my PLC class and things like that, and I've been spending a lot of time trying to get a PLC simulator and stuff like that. So I'll try to get it up there, but chances are it's not going to be up today. Any other questions? I have not. I started looking at the exam, but I did not get through all of them either. So I started going in and adjusting points, but I haven't done that. I can say I apologize for that, but it's just amazing to me how much time I've been spending trying to find simulators or work and other things. So please bear with me on this. I will go through and look at those exams and adjust points. So. All right. If you have any questions, email me. If there's something you're really confused on, we can do a one-on-one session like this. If you want to do something like that, let me know. Otherwise, Monday I do plan on doing the